To our second talk on MEP related research. This is from Tim Jupp at the University of Exeter, and this relates to a point, to some extent, to a point that Jeff, who's not even looking, made on page 1, which is about rotation rate. Actually, why rotation rate doesn't appear in these models. So, Tim, over to you.
Okay, thank you very much. Thank you very much for the opportunity to speak here. It's also a pleasure, I think, to be taking part in my first webcasted seminar. I don't know if you've had a look on the web, but if you click on someone's seminar, there's a little intro from, I think, Stephen Fry at the beginning. So thank you, Stephen. I'm going to talk about MEP and planetary climates, insights from a 2-box climate model. That's very much along the same lines as what Axel was just talking about. And I'm going to put in some very, very simple atmospheric dynamics, because you may have noticed that in all the discussion of 2-box models so far, nobody has made any constraint about what is actually dynamically possible for the atmosphere. What I'm going to talk about towards the end of my talk is all summarized in full gory detail in a paper that Peter and I published this year in Phil Trans B. But I shall try to excise the gory detail in this talk. Before I get on to what's in the paper, I thought it was worth revising for a few minutes what is really a terminological minefield to do with entropy and entropy production. So there are different ways in which people appeal to the idea of entropy. Boltzmann would talk about a maximum entropy state. Edwin Janes would talk about the general procedure of max-ent inference, which is about assigning probabilities to microstates. Prigogine talked about minimum entropy production. Roderick Dewar would talk about maximum entropy production. It's pretty confusing already. A major potential source of confusion is that there are really 2 entropies, and we should work very hard to distinguish them. There is thermodynamic entropy, which for the moment I'll call S, which has SI units of joules per Kelvin. And then there is information entropy, S sub I, which is dimensionless and a property of a distribution. We should also briefly keep in our minds 2 different types of steady state. A system in thermodynamic equilibrium, like a gas in a box, is closed because there is no transfer of energy or mass across the boundaries of the system. And we should contrast this with a non-equilibrium open system. And the thing I always have in my mind for these is convection. Convection between a hot plate and a cold plate. So, thermodynamic entropy in joules per Kelvin, if you want to take the microscopic view of where it comes from the fact that a macro state, something that is well defined on the macro scale, might be reproduced by many omega microstates. So there are many configurations of molecules of gas in a box which on the macro state look exactly the same. And the thermodynamic entropy in joules per Kelvin is the Boltzmann constant in joules per Kelvin times the logarithm of the number of microstates yielding that macro state. If you want to take a macroscopic engineer's view of what thermodynamic entropy is, and we've touched on this already this morning, you change the entropy of a system at absolute temperature T when you add a quantity of heat to it. So that's why it's joules per Kelvin. We talk about maximizing entropy production. So we're talking about maximizing the rate at which thermodynamic entropy is produced. And this is very, very similar to what we've already seen from Axel and Roddy in this workshop. If you have some sort of heat engine or something going from a hot temperature to a cold temperature, then the rate of entropy production in watts per Kelvin integrated over the volume is the integral of a flux times a force. That's very fundamental to this whole idea. It's fluxes times forces. Okay, let's contrast all that thermodynamic stuff with the Shannon information entropy of a distribution. And I want to take a couple of minutes to go quickly through my favourite heuristic argument for why this is a sensible thing to look at. This is an argument due to Wallace, which you can find in the book by Janes, which I'll talk about later. So suppose we have a lot of different microstates, and this could be different configurations of molecules of gas in a box, or it could be different configurations of moving molecules in a convecting system. So there are all these different microstates that the system could be in, and I want to have a procedure for assigning a probability distribution across all these different microstates. And I'm going to apply some macroscopic constraints. I say, whatever the distribution is, I want it, in this example, to have some mean mu and some standard deviation sigma. And one way you could generate a probability distribution over microstates is to take lots of little quanta of probability. I might have n of them, so they each have probability 1 over n associated with them. And I'm going to scatter these quanta of probability across the microstates at random. And then I'm going to see which of the distributions I can produce by that procedure satisfy these constraints. Okay? So I could produce essentially an infinite number of distributions by scattering a very large number of quanta over microstates each time. I only keep those distributions that satisfy my macroscopic constraints. So here's a gratuitous animation. It just allows me to have a drink, actually. A gratuitous and slightly too slow animation. You get the picture, right? There it is. So let's suppose that these three distributions on the left have the right mean and variance, and the one on the right doesn't, so I'll throw away the one on the right. Oops. But then I might look at the set of all distributions that satisfy my constraints. Sparing you the detail, this turns out to be a multinomial problem because you're throwing quanta into a discrete number of boxes, so there are lots of factorials involved, so you're going to need Stirling's approximation. It turns out that the distributions you get that satisfy your constraints are close, in some sense, to the distribution that maximizes the Shannon entropy. Okay, so that's why we like the idea of maximizing the Shannon entropy. It seems like a sensible way of assigning probabilities to a set of macrostates given some constraints. Okay, going back to thermodynamic entropy, I can do this quickly, I think. We don't need to spend too long on this. So I just want to draw, again, the distinction between a thermodynamic equilibrium state. So this is gas in a box. I've got blue gas on the left, white gas on the right. Over time, the gradient is smoothed out, and so the entropy of this system increases over time. I want to remind us that we're thinking in our case about open systems for which the prototype is Rayleigh-Bénard convection in a cell. In this case, motion is driven by the temperature gradient between the bottom and the top. There is a conductive state in which the energy is transferred solely by conduction. But if you crank up the temperature difference to some sufficiently high level, that means cranking up the Rayleigh number to some sufficiently high level, you get convection. And you can think about where entropy is produced in this system. And essentially it's produced in the boundary layers. So something that people look at in fluid dynamics is the total rate of entropy production as a function of Rayleigh number. So this is how strongly I'm driving the system. And there is a solution of the equations, which is unstable, in which there is no fluid motion. So heat transfers by conduction only. That's this line here. But we observe that above the critical Rayleigh number, the rate of entropy production is greater than it would be under conduction alone. And we might wonder if this is a state in which entropy production is maximized. So what I want to do here is say something rather speculative. I find all of this stuff fascinating. I also find it's seductively fascinating. I don't think we're at the stage where we know any of this stuff very certainly. But my interpretation of what I read, it goes like this. There are various states that the system might be in. Let's think about convection in a box for now, but it could be the atmospheric heat engine. And associated with each state, and the state might be steady or it might be non-steady, there is a rate of thermodynamic entropy production. And I hypothesize from what I've read, though I don't quite understand this fully, that Prigoghine's idea of minimum entropy production says that steady states are local minima in this entropy production curve. Okay, so these are allowable steady states of the system. But when you run an experiment and it's macroscopically reproducible, you tend only to pick out one of these steady states. So you don't pick out the conduction only example for a sufficiently high Rayleigh number. You pick out one which we hypothesize might be the one that maximizes entropy production amongst the class of local minima, amongst the class of things which are local minima in entropy production. It's rather speculative, but I thought it was worth saying. So an ongoing challenge that we've alluded to already in this workshop is what is the link between information entropy SI and rate of thermodynamic entropy production, which I'll call S dot. So Roderick Dewar has made more progress than anybody on this. And the idea is this. Maximizing information entropy seems like a very sensible way of assigning probabilities across microstates. We suspect, based on what Roderick says, amongst other things, that this is somehow equivalent in practice to picking out the macroscopic steady state in which the rate of thermodynamic entropy production is maximized. And somehow, in a way that I don't fully understand, the constraints that you choose to impose when looking at it from an information theory perspective induce thermodynamic quantities that will be maximized in the state that you observe. We had a bit of a debate already about whether you're maximizing dissipation rate or entropy production. It's a bit of an open question. But let's proceed anyway. For the remainder of the talk, essentially, I'm just going to ask what happens if you take this procedure off the shelf. You just say, all right, I'm going to maximize entropy production and see what happens. I wanted to draw your attention to a couple of good overview papers that talk about the idea of maximum entropy production in the context of climate. So Ralph Lorenz wrote one called Full Steam Ahead, probably, very easy to find. There's one in Nature 2005, Order Out of Chaos. And I also want to recommend, if you're interested in this sort of thing, I keep talking about the book by Jaynes. I mean Probability Theory, The Logic of Science by Edwin Jaynes. And Axel Kleiden and Ralph Lorenz put together a compendium of articles on entropy production a couple of years ago, which I also recommend. So Axel has already mentioned this idea of the Earth overall being a producer of entropy. Energy comes in from the sun at sort of 6,000 Kelvin. All sorts of processes go on that create thermodynamic entropy, and then heat is rejected to space. So it looks as if perhaps MEP is useful because we can use it to suggest parameter values. If we've got some model with a free parameter that we vary, we might just observe that there is some value of that free parameter for which the entropy production is maximized. And if you believe in this system, you would say that if MEP gives me the observed value, then whatever my model is a sufficient description of the system. Sufficient in the sense that everything's macroscopically reproducible. If this procedure doesn't give me the observed value, then that suggests something is missing from my model. There isn't enough physics. Okay, so we're going to think about the atmospheric heat engine. Exactly as we heard about before coffee, we're transferring energy from the equatorial region to the polar region. I call this the Mark I atmospheric heat engine because really, if you put some dynamics in, the physical balance is hot air rises is balanced by surface friction. Let's make this a little more complicated. We'll go to the Mark II. The Mark II atmospheric heat engine adds in the idea of Coriolis forces. So because of the rotation of the Earth, which we all suspect has to be relevant somewhere, we're going to allow for the fact that winds are deflected. It's slightly misleading. This is a good point to make this observation. This picture of the Mark II heat engine shows a number of Hadley cells in each hemisphere. To make life easy, I'm only going to talk about having one Hadley cell in each hemisphere. But we'll get on to that in a minute. Okay, so there are various climate models out there that invoke MEP to fix the value of some unknown parameter. At the simple end of the spectrum, Ralph Lorenz did a two-box model which contains no dynamics whatsoever. He just tunes the flux from equator to pole in the atmosphere to maximize his entropy production. At the more complicated end, and it's good that Axel's already mentioned it this morning, Axel took a numerical model, a simplified GCM if you like, and he played around with the von Karman constant, and he found that the true value of the von Karman constant maximized his entropy production. And I wanted to put myself in the middle of this spectrum by putting in the minimal amount of dynamics to go beyond the no dynamics model without getting into complicated numerical simulations. So, Ralph Lorenz's model, which is in GRL 2001, is like this. There's a tropical region that receives and emits radiation. There's also a polar region. There is conservation of energy in both boxes, and there is some flux F carried by the atmosphere and oceans, we imagine, that transfers energy from this region to that region. It's got no dynamics whatsoever, but what you could do is solve the system with this equator to pole flux F as a free parameter and just see what value of F maximizes entropy production. A notational point, sometimes people express these things not in terms of the flux F, but in terms of some effective diffusion coefficient D. So you might assume that the flux is proportional to temperature difference with some constant of proportionality that's like a diffusion coefficient. Or you could just define your diffusion coefficient to be your flux over your temperature difference. So I'm going to call solutions of this model Lorentz energy balance solutions, LEB solutions. And the big story is that to get these solutions, you take outgoing radiation, which goes like temperature to the fourth, you linearize it, just to make life a bit simpler, And the whole system is driven by the contrast in incoming fluxes I0 minus I1 between the two regions, which I'm going to call F sub EP. My notation from now on is that a subscript EP denotes an equator to pole difference. Subscript E is the equatorial region, subscript P is the polar region, subscript A talks about the atmosphere, and a subscript SA is some difference between surface and atmosphere. We'll come back to that in a little while. Lorenz's solution is in his paper. I found it very helpful to non-dimensionalize his argument. This becomes more relevant later when we put dynamics in. Several people already have talked about memories of Cambridge, which are stirred by being here. I learnt two very important lessons during my time as a student in Cambridge. The first one is that I'm really not very clever. And the second one is non-dimensionalizing physical systems is the path to enlightenment. So that's what I did. And in this case, it's rather trivial, but it'll become important when we add the dynamics in. So my dimensionless rate of entropy production I'm going to call sigma dot, and it turns out, when you've non-dimensionalized, to be the product of a flux and a driving force. So that's the atmospheric flux times the equator to pole temperature gradient. The energy conservation constraint in dimensionless terms is simply that the flux plus the force equals 1. And it's something to bear in mind that if we do this LEB solution with no dynamics, we just maximize entropy production, the solution that maximizes entropy production has the flux equal to the force equals a half, and it has entropy production 1. Okay, we'll compare later when we put some dynamics in. And we've seen this before. This is what happens. Here's the diffusion, or the flux, if you like, that you vary. As you vary it, the polar temperature follows this blue line. The equatorial temperature follows the red one. So when you transport lots of heat, equator and pole have the same temperature. When you transport no heat, everything's in radiative equilibrium. So there's a big contrast in temperatures. In between the two, there exists an optimum where the entropy production dotted is maximized. Okay. And we saw in Roderick's talk that what was interesting about the LEB solution, Lorenz's solution, was that he tried applying it not only to Earth, where it seems to work at reproducing equator to pole temperature contrast, but also in other rocky planets and planets' moons in the solar system. So here's the case for Titan. Again, polar temperature, equatorial temperature. Here are the observations of polar and equatorial temperature, and they seem to coincide roughly with the point at which the entropy production is maximized. Same thing for Mars. Yeah, same thing for Mars. And it's weird that we get this result without having any dynamics in it. So to summarize the Lorenz model, it seems to give you the right answer, which is terrific. But why? It's the kind of thing that drives you nuts in the middle of the night. How on earth can it give you the right answer? Surely the atmospheric dynamics matter. Surely planetary rotation rate matters. Okay. Let's go on to the model at the far end of the complexity spectrum that I showed you earlier. Another gratuitous animation. So Axel, GRL 2006, took the Puma model and he tried varying the von Karman parameter. It always made me very uneasy at the thought of varying a constant. People sometimes call it the von Karman constant. If it offends your sensibilities, you can imagine that he varied the roughness length instead. So he grew a lot of trees, or he chopped trees down, made the surface rougher, and increased friction between the surface and the atmosphere. And here we are. So he varied the von Karman parameter. There's the true value. And what do you know? That coincides with the simulation in which entropy production is maximized. Well, that's terrific. But why? Why? Which model parameters are important here. Well, maybe non-dimensionalizing will help us on that one. And this question of what does it even mean for the surface friction predicted by MEP to be different between planets? I don't claim to answer these questions, but I raise them. So here we are. Here's the model that Peter and I came up with, and it's as follows. We're going to be very much like the Lorenz two-box model in the sense that we'll have an equatorial region and a polar region. If we divide them at 30 degrees latitude, that means they have equal surface areas, which is a nice symmetry. We're going to imagine that the contrast in surface temperatures sets up a single Hadley cell in an atmosphere of thickness h, where the planetary radiuses are, and the effect of this hemispheric Hadley cell is to induce a surface wind that blows at an angle theta to the north-south line, to meridians. So, of course, this surface wind going from pole to equator is balanced aloft by some return flow from equator to pole. And the net effect of that Hadley cell is to transfer energy from the equatorial to the polar region. We're going to treat surface drag coefficient, CD, as a free parameter. We're going to cook up a model and solve for the wind speed u and the angle away from meridians theta. It's helpful to have a schematic of exactly what's going on. We probably don't need to worry about what everything in this diagram is. But the idea is, here's our equatorial surface at temperature TE, our polar surface at temperature TP. These dotted lines are radiation. So there's incoming and outgoing radiation, which is, the outgoing is linearized. I've got this Hadley cell shown schematically here, which carries a flux, F sub A, that's atmospheric flux, from equator to pole. And these boxes here are meant to represent the atmosphere. So if the equatorial surface is at temperature TE, the equatorial atmosphere is at temperature TE minus some surface to atmosphere difference. And symmetry in the problem means that it's plus TSA on the other side. Makes life a bit easier. Okay. Yep. So the physics here is that there is a drive for a convective cell, because this is hotter than that. There is friction slowing down the wind. Okay? Surface friction slows down the wind. So there turn out to be 5 governing equations. Here they are in dimensional form. Energy is conserved, and it turns out when you do that, you only need to worry about equator to pole differences. There has to be the flux of energy has to be carried from the surface into the atmosphere. So I assume that this is proportional to the speed at which the wind blows, because the faster the wind blows, the greater the heat transfer between the surface and the atmosphere. Proportional to the surface atmosphere temperature contrast. Rho c is a heat capacity, get the dimensions right. CD is some drag coefficient, whatever that means in a simple model like this. This equator to pole heat flux balance is just a balance that says the total heat flow rate that goes up here is the same as the heat flow rate that goes through here. So it says the rate at which heat goes from the surface to the atmosphere, that's why there's a pi r squared in there, is the same as the rate at which heat is advected, that's why there's a u, across, this turns out to be the temperature difference between the two atmospheric boxes. The cos theta, of course, is because the wind doesn't necessarily blow straight polewards. Okay? The dynamics, I have 2 dynamics terms because I have a zonal term and a meridional one. The balance here is quadratic drag on the surface, that's why there's a u squared here, is balanced by a pressure gradient. That's this thing here. That's why gravity is important. More gravity, more pressure gradient. And a Coriolis term. That's where these omega u's come from. So, We're going to treat surface friction as a parameter we can vary, just play with it, see what happens. We're going to deduce surface temperature, atmospheric flux, and wind speed, and we'll just see what happens. We could ask, what values of drag maximize the entropy production? We might ask, what values maximize the atmospheric flux? Now, it turns out that you can solve this system analytically, and the details are in the paper, but I'll try to give you the important summary. So, it turns out that these are the dimensionless parameters that matter. Actually, eta, the dimensionless thickness of the atmosphere, doesn't matter to what I'm going to tell you, to what I'm going to go on to explain. It's there, but it sort of drops out of the equation. So don't worry about eta, but recognize that the dimensionless thickness of the atmosphere is relevant. The ones that really matter are psi and omega. So psi I call the advective capacity of the atmosphere. And it's a measure, if you like, of how much energy the atmosphere could transport from equator to pole under gravity-driven flows. So intuitively, that's why the heat capacity of the atmosphere, rho c, matters. It's why gravity matters. The thickness h of the atmosphere matters. Omega is a dimensionless rotation rate of the planet. I mean, root gh is a speed, omega r is a speed. You can interpret this as being the ratio of a Froude number and a Rossby number, I think. Anyway, this thing gamma is just a geometric constant that comes from the geometry of the problem. We're on a sphere, so there are pi's and so on in here. But we can ask, what happens as a function of these dimensionless parameters for an arbitrary planet? I don't expect you to take these numbers in, but the point is that all the numbers that appear in my original formulation of the problem up the top for Earth, Titan, Mars, and Venus can be mapped onto my dimensionless parameters down the bottom. And you can do that for any planet you like. And this is the solution you get. So this comes from an analytic solution. There's no point giving you the equation except in the paper, but here's the picture. What happens as I vary the drag coefficient? Okay, so here's the wind speed. And the wind speed, of course, is the square root of the sum of the squares of an east-west wind and a north-south wind. So there's the east-west wind, there's the north-south wind. So unsurprisingly, if I have a very high drag coefficient, there isn't much flow. The wind speed is very slow. As I reduce the drag coefficient, I get faster and faster winds. And the balance between north-south and east-west winds is, of course, given by this angle, theta. The theta scale's on the right-hand side. So over here, I have predominantly zonal winds, and over here, I have predominantly meridional winds. So we can see straight away that in this balance with Coriolis force, surface friction, pressure gradient driving everything, there's a point at which the wind speed, at which the north-south wind speed is maximized. And of course, it's the north-south wind that carries energy from the equatorial to the polar region. Now, this was a surprise. Didn't expect this. In the case of the Earth, so the LEB state, the state Lorentz would have got by not worrying about the dynamics at all, is one in which the entropy production is this double-humped solid curve, is 1. So he'd have said, this thing must be 1. And it turns out there are 2 states in this system which can achieve an entropy production of 1. And they're shown by the red dots. The MEF state, the state at which the atmospheric flux is maximized, is shown by the blue dot. So atmospheric flux is this dotted line. Okay? So, in a sense, we get the same result as Lorentz. We get that our system is capable of producing an entropy production of 1, which is what he claimed it would be without worrying about the dynamics. It is intriguing, and I don't have a good answer to this, that there seem to be 2 states in this model which give me an entropy production of 1. One with rather zonal flow and one with rather meridional flow. I don't particularly understand that, don't claim to, but I think it's interesting. Now it turns out that if you do this game for the other rocky planets, you get a very similar answer. So I'm going to show you several graphs that are essentially the same. For Venus, the entropy production, the double-humped solid line, can attain the value 1, which Lorentz would have predicted with no dynamics. The same is true for Titan. So it would appear that these dynamics that we've put in do not constrain the maximum achievable entropy production. Now, Mars is similar, except that Mars is right on the boundary of things. Okay? The 2 MEP states, the 2 red dots at the top, have almost coalesced. And it would turn out that if we changed our parameters a little bit for Mars, this entropy production curve, the solid one, would no longer reach all the way up to 1. So if we changed our parameters a little bit for Mars, we'd end up with a planet where the dynamical constraints prevented the entropy production predicted by Lorentz. And a way of interpreting that, if we go right back to the beginning, I said that you get an entropy production of 1 when the flux, dashed line, is a half. And if you tweak your parameters a little bit, this flux no longer is able to reach up to 1/2. And that's why, hypothetically, there might be planets for which an entropy production of 1 is not possible. So because we have an analytical solution to this simple system, we can look at a parameter space of our rotation parameter for the planet against our advection parameter. And we can say, given omega and psi, what is the maximum achievable entropy production that you can achieve by tuning surface friction? And these are contours of that maximum achievable entropy production. And it turns out that in the top left of this parameter space, when rotation is sufficiently small and advective capability is sufficiently high, it is possible to choose a value of the friction for which the entropy production is 1. So that's what happened for all the planets in the solar system that we looked at. It so happened that they live in the top left of parameter space. So let's show that explicitly. So this curved line, I call it the critical line for obvious reasons, is the line separating the region from which the dynamics affect the MEP state, down here, from the region in which the dynamics don't affect the MEP state. When I say affect the MEP state, I mean affect the value of entropy production. Of course, the specific dynamics in here are relevant to what the wind speed is and what the angle of the wind speed is. But if we just ask what is the maximum achievable entropy production, the dynamics don't matter above that line. So Earth, Mars, Venus, and Titan, P1 is a hypothetical planet. So in the paper, I won't show it now, but we imagine a hypothetical planet P1 with these parameter values in which the dynamics would affect the MEP state. So I just want to summarize what we found, really. We thought about maximum entropy production states, where you maximize sigma dot, subject to energy and dynamics. we started from Lorenz's box model, in which his only constraint is energy, but he's also maximizing sigma dot. And we observed that there were also solutions in which the atmospheric flux was maximized, MAF, maximum atmospheric flux. It turns out, and the details are in the paper, this is the important sentence at the bottom, the MEP solution is equal to the Lorenz solution if a Lorenz solution exists. So if there is a solution for which the force and the flux are half and the entropy production is 1. If no such solution exists, then the MEP solution is the maximum atmospheric flux solution. Okay, and I'm almost done. This is just another way of expressing the central idea that we had. Lorenz, in his model, parameterized the flux by looking at a coefficient of meridional diffusion, effectively. That was his big D. He said that the flux is D times the driving force. So if we look at things in those terms, when we vary our one free parameter, we're varying this coefficient of meridional diffusion. And if there were no dynamical constraints at all, then this is what things would look like. Here is the entropy production, the solid line. The flux is this dotted line, and the driving force is this complementary thin line. So the effect of adding in constraints is to make high diffusion coefficients dynamically impossible. Okay? So whenever you put dynamics into your model, this is just an example, so it just happens to be 20 here, but that's an example. In this example, whatever dynamics I put in meant that I could have any diffusion coefficient I wanted as long as it was less than 20. But that diffusion coefficient includes the case in which the entropy production gets to 1. So that's the same as the answer we would have got without dynamics. If we'd had some other constraints, this dynamically impossible boundary might have been back here, and then the dynamics would not have allowed us to reach entropy productions of 1, would have been constrained to a maximum entropy production down here. Okay, that's essentially all I want to say. To summarize, we tried to give some insight into a numerical result of axles. We felt that we'd confirmed what we wanted to, which was that the no dynamics result of Lorenz is the limit of a dynamical model, as it really has to be. And we tried to gain some insight into how the MEP state is affected by the dynamics and the rotation rate that we put into our planetary model. And I'm going to finish with one more slide. People have said this already, but I'd like to re-emphasize it. My feeling is that MEP tells you when your model contains just enough physics. And I know that we may have a discussion about what's a good model and what isn't, but I like models that contain just enough physics. Thank you.
I want to ask a question, but could I ask a precursor question just to clarify in my mind? So going back to your right at the beginning, you were talking about Rayleigh convection.
Yes.
And you noted that there was a critical Rayleigh number which corresponded to the onset of convection,
yep,
for which the entropy production was larger than for the sort of heat conduction, I suppose, case. Actually, the precursor question was, is that critical Rayleigh number predictable by MEP methods? I mean, can one predict what value that occurs, or is one just saying that exists somewhere?
Well, it's usually predictable by a stability argument.
Yeah, I know. But
So I wonder if stability arguments are sort of the same as MEP arguments. I mean, Roger was talking about this earlier. I don't know is the short answer, but I see the point you're
Because, well, the point I want to get to is that for the atmosphere, there is something similar, which is the onset of baroclinic instability, which, again, presumably, for a given temperature gradient and rotation rate and so on, the baroclinically active solutions will have a greater entropy production than the ones which aren't.
Mm-hmm.
Now, insofar as your model, as far as I could tell, didn't incorporate baroclinic instability, it was just the kind of Hadley cell
Yep.
type thing. You're sort of, am I not correct then to say what you're really looking at is that lower branch of the, for the atmosphere, and not the true maximum entropy production branch? All your calculations are not really dealing with maximum entropy because you're not dealing with the sort of actual baroclinically unstable atmosphere which we see in reality.
So I think the question is, what can my model reproduce? What's the minimal amount of stuff I need to put into my model to reproduce something? And I wanted to reproduce the equator to pole temperature gradient. And Ralph Lorenz seemed to show that you don't need dynamics to do that. And I tried to justify why you don't need dynamics. So it would appear, because we get the right answer for Earth, that we don't need to worry about the onset of baroclinic instability
Except
to get the right answer. But then the question is why? So
If you had an equivalent problem for convection, presumably it is important if whether you're considering the upper branch or the lower branch of that.
well, then the question is whether or not
Yeah.
this analogy is relevant. I mean, when I introduced this idea, I just wanted to motivate the idea of non-equilibrium open systems. I confess I hadn't thought about how deep an analogy there was between turbulent,
I guess the
non-turbulent
point you're
convection.
making, Tim, is that that dynamics, simple dynamics in there may be over-constraining the problem actually, because you don't have this ability
Yeah.
to have baroclinic instability. Quite possible. Thanks.
Yeah, just as a thought, I mean, also you assume that all the dissipation takes place at the surface.
Yep.
You know, the present day atmosphere, half of it is dissipated around the jet stream. And that might have to do with the baroclinic instabilities as well.
Okay.
This is a comment, you know.
Yeah, fair enough. I mean, I fully accept that there's all sorts of extra stuff that you could put in, but it all depends what question you're trying to answer. And if you want an intuitive reason why rotation rate doesn't seem to matter and dynamics don't seem to matter, I would argue that you want to go with the simplest thing that gives you insight.
In the examples for the planets where you have double maxima,
Yes.
what is the dynamic difference between the two states?
My guess,
Is it like in the Maynard convection, is pure conduction and some more complicated state?
my guess is
Maybe
it's to
one
do
is
with what
stable,
I,
one is unstable.
I imagine it's to do with what is balancing what in my equation. So I've got surface drag, pressure gradient, and Coriolis force, and I wonder if they are two extremes in which two of those things are balancing each other.
Have you actually solved those to see what's happening?
I don't understand what you mean by solved.
No, like in the Puma model, you run something and you can see what the configuration is. Have you done?
Well, in the I've solved this model completely. So given parameters, I can tell you exactly what all the unknowns in the equations are. Perhaps I should think a bit more deeply about what it means.
There was one here, I think.
I was just wondering if some way to bring some biology into this, if you were to have a different CD drag coefficient for the polar regions and one for the equator, whether there would be something optimal to tell you why trees are higher around the equator. Whole. I just wondered if that might be a way of achieving it.
Well, that would be fun to do. I'm not sure it would tell you why trees are higher, but it would be a way of encoding minimally the fact that trees are higher in the
There's
equatorial
nothing
region.
optimal that might tell you that.
Well, with all this stuff, you suck it and see. You try it.
Yes, yes.
And if you get the right answer, you deduce, oh, well, that's obviously all the important macroscopic constraints, isn't it?
That's a great answer.
I have kind of two questions.
Yeah.
They're a little bit general, so perhaps they're for this afternoon rather than for right now. But one of them is it really the case that maximum entropy production is a corollary, if you like, or follows directly from maximum entropy itself? If that is the case, then it's an enormously powerful axiom almost that should apply to everything. It seems very important.
Do you want me to answer that one before your second question, or do you want to ask the second one as well?
By all means.
Yeah, so I think it's fair to say we don't know if they are exactly equivalent. We strongly suspect it, and Roderick is the man to go into more detail, I think, if you wish to.
Not no.
Okay, we'll discuss it this afternoon. But I agree with you, yes. If it can be proved, we're away.
Well, maybe we are, because that's my second question. Then, if it is a content-free theory, which is good in a way,
You've got to be wrong in that case.
then you can't be wrong. Then if you are wrong, you just haven't got enough constraints. So how on earth do you figure out what constraints? You just wait until you have the right answer. I mean, is there any a priori way of figuring out the constraints? That would make it into a theory rather than something,
Well, my feeling is that you figure out the constraints by using your skill and judgment. So I always go back to the analogy of Rayleigh-Bernard convection and/or gas in a box. You just observe with gas in a box that the gas law works. So the parameters in the gas law are sufficient macroscopically and save you the bother of doing a molecular dynamic simulation to work out what happens in a box.
I think it's class first.
Do you feed back the dissipation into the system?
No, and perhaps I should.
It could explain the two.
Yeah. I've worried actually that on a related note, that I didn't apply a second law constraint here, which I possibly should have done.
Because we do it in Puma.
Yeah.
Right.
Cool.
That's interesting.
Well, I guess I was picking up on the gas in a box theme, and you sort of said there's no. The maximum entropy relieves you of the need to do molecular dynamics, right? You might turn that round and say, one of the reasons why we believe thermodynamics, right, or we didn't stop believing it because people did molecular dynamics calculations, and what they observed was the predictions of statistical mechanics, of course, with fluctuations about statistical mechanical equilibrium, right? So in other words, the paradigm survives in a system where you've got gas molecules exchanging energy and stuff, right? So one question would be, can you think of a correspondingly simple non-equilibrium system where you could, the molecular dynamics of fluxes or something, because that's what you're really appealing to, where you could demonstrate similar sorts of applicability and also limitations of the idea. Because I think one thing I find difficult is it's very well to say this works for all these systems, right? But I think in most sort of aspects of physics, we also want to have examples of where it doesn't work, right? Because that kind of helps us understand, right? And so the question would be, statistical mechanics doesn't apply if you only have two gas molecules in the box, right?
This sounds like good
when does
stuff.
maximum entropy production not apply?
Yeah, no, I think that's a good point. I'd like to sort of maybe spin that into this afternoon, because they sound like big questions that are associated with how we would use this approach. Roddy, did you want to?
No, I'll follow up after something.
Okay. Yep. Tim?
I have another question which is slightly tangential, I think, but I just want to raise it. Your example, just the simplest example, where you had, again, gas in a box, and you said the maximum entropy state was where basically the molecules are distributed evenly around the box. Now, if you switched on gravity, I mean, if these were self-gravitating objects, then they'd all clump together.
Yep.
And so then you have to ask yourself the question, is that violating the second law of thermodynamics? Or do we need to additionally consider some entropy associated with gravity? Now, I only raise this point because you mentioned gravity in some moment in your talk.
Yes.
And I'm just wondering, I don't really know the answer to this question, but I'm just wondering whether gravity is something you can sort of ignore, or whether it plays a role that hasn't been put in. Because it seems in very elementary considerations, gravity absolutely, the gas in a box example, gravity changes things dramatically.
Yeah. I have no answer, but I agree it's an interesting question.
Just a quick suggestion, in that context, would that be another dimensional variable that you'd then have to go and do the dimensional analysis again, and possibly that would, it's the same as when you say put a magnetic field on turbulence, you go from, Kolmogorov theory to MHD turbulence theory, and if you do the dimensional analysis, you add an extra, you go from whatever it is, 3 to 4 dimensionless combinations. I mean, presumably you've done this, and
With gravity, you mean?
Sorry, I'm saying presumably you have done it without gravity, but you if you then put it in.
If there's no gravity, there's no drive for the atmosphere to flow. That's the argument.
But you see what I mean? You
I do.
introduce these things explicitly through the dimensional prescription that you're doing, which is one of the great strengths of it, that you can keep track of these things.
I was just a comment about the planetary rotation rate, which you said if it's fast enough can impose then the dynamics can constrain the system. And just comment that we know the moon formed 4.4 billion years ago in a collision with the Earth, and initially the Earth was spinning a lot faster and has steadily spun slower as the moon has moved further away. I know that probably orders of magnitude would be required, but
well, I was going to say, I was just about to ask
because it makes you think about Mars, which has moons, of course, but I don't know how they formed, and presume it could have been a different way, but it sits right on the cusp there, right?
Are they very light mass though?
So just more generally, just thinking about that, as was interest in extrasolar planets as well. We can, I should think we can at least conceive of that. If not in this solar system, we presumably can conceive of systems where, if you're a simple model, then the spinning would be so fast that it would constrain the system.
Yeah, sure.
A last one. It's about March. I remember vaguely that Ralph Lauren had to, wouldn't say cheat, but I mean to make sure he's counting everything, and there was a problem with the solid ice.
Right.
Which sort of goes beyond your fluid model. So how do you reconcile these two options? So just to make things clear, when Ralph Lauren first tried his two-box model on March, it was first not maximizing entropy production, and then he remembered that March is a bit specific because there is not water precipitation like on the Earth, but ice being sublimated from one pole to the next. And when you take into account that extra entropy production, then you arrive at MEP. So can you comment a little bit on that?
I'm not sure I can. So are you saying that whatever parameters Ralph picked for Mars, which of course I just stole from him, you're saying they take account of some extra bit of physics that he...
It's I don't want to be bad. I remember that he had to go through a two-stage process, and his first trial was not convincing.
It's not Venus, is it?
That was
It's
Mars.
definitely Mars.
It is about
the ice.
sublimation of dry ice.
Okay, yeah.
And I don't think it's included in this actually, so that's an interesting thing to look at, is whether, because Ralph didn't get, as you said, he didn't get a realistic state of an MEP state for Mars. Right. We probably should wind it up now. Thanks so much for all the discussion. We'll hopefully spin some of this up this afternoon. We've got lunch until 2 now, so see you back.